morning. I will try to introduce you to some recent subject in mathematics, which was born basically at the end of the second millennium. And the main provider for the theory at that time was someone whose name is not very well known to physicists. His name is Terry Lyons. He's not related to the French Lyons family. Okay, so why do I give these lectures? First of all, because it's something I think is rather new, as I said, and interesting, and also because somehow, even if it's a mathematical theory, it has some flavor of physics, and I will try to insist on that. And mainly, what I will try to explain is that the intuition as physicists that we have of the renormalization group is somehow finds one of its simplest avatars, let's say, in half-path theory. So that's the first motivation for me to give the lectures. Another motivation is that when I first heard about rough path, it was maybe 10 or 15 years ago, I really couldn't understand at all what mathematicians were saying. And it was really hard, trying to read or listen to seminars. And of course, after a while, I started to think about myself with the help of notes. And it took me hours to understand what was going on, even if in the end this is basically simple. And once you've understood, as often happens in physics or mathematics, once you understand, you realize that in fact what you did not understand, you don't understand why you didn't understand before. So I decided to give a presentation which is rather different from the presentation that mathematicians usually give. And I hope this will be helpful for some people so that they will waste less time than I did. But I realize now that, in fact, the textbooks are excellent once you understand. So either to start if you don't like my way of presenting, or to get deeper, I can refer you to two books which are essentially, as far as I understand, the only textbooks. So let me give you the... I don't have them. There is one written by it's error, and the name is A Course on Rough Path. It's Springer. And the second one is the same first author, and I think it's called Multidimensional Stochastic Processes. As rough path. And this one is slightly more advanced. And if you're interested in the subject, you should have first a look at this one. But this one is both are very good. And okay, so what I'm doing I will cover really a very small part of what these guys cover, and I will try to be a little to have some originality, which is I don't know if it would be good or bad, but it's supposed to be a bit. As the subject is not very familiar, I hope that will interrupt me as soon as I say something which is for you mysterious, because that's the only way I can keep you with me. So don't hesitate to interrupt me and ask questions. So just to say how the lectures will. Okay, so to be concrete, I will try to put notes. I don't know if there is an official way to do it, but I have a web page, a piece on the website of the lab, which is well, anybody can have a look at it, and I will put.
We will relink it from your course page.
Okay.
You have a course page. We will link to your.
Okay, perfect. Okay, oh, okay, I will put it directly in the course. Okay, so there will be lecture notes, at least for the first lectures. I mean, I realize that it's a big work, so I hope I will be able to keep the pace, but okay, I'm not totally sure, but I hope to do so. So what I will do today, to start with, so there will be a long, in fact, discussion of motivations, and then I hope to be able to do it today, define formally RAFPA. But in fact, once we've gone through the motivations, you will have a precise idea of what a rough path is. So that should be okay. And then, if really I'm very fast, which I'm pretty sure I will not be, then we will give the simplest example. If not today, then next time. And then we will spend, I will not give a precise, but then we will give an integration theory for RAFPA, essentially. And there will be a few, well, quote unquote, physical applications, and I will try to make things in such a way that the first hour will be the most demanding. There will be concepts, and it may be hard at some points, even if it's not so hard. And then the second part will try to give illustrations. That way I will be able to deal with the simplest example today, but I'm not sure I will be. But there will be essentially two main examples that I will try, which are related to physics. One that I call with Brownian motion. So I will explain what this means, but well, it's about dancing the valse as a Brownian walker. And the second one is Brownian motion in a magnetic field. Okay, so this is for today, and this will keep us busy for the next sessions. This is made of several parts, and I will give more details. But today we shall focus essentially on motivations. So is there already a question? I've said nothing, but why not? So let's start with the motivations. So this is, in fact, I don't know if I'm right or not to do it that way, because this motivation section is going to be a bit, well, technical, but it's basically simple. So, well, why not do it? Because it really leads to something important in the end. Okay, so what is the basic idea? Is essentially is that in mathematics and physics, many things are defined via a limiting procedure. If you start, for instance, thinking about even simple things as Riemann integrals, what you do is you do certain sums, you take a limit and you get the integral. And of course, the sums you could explain basically to, well, anyone, 10-year-old kid, and then the notion of limit is a bit more demanding, and there is some price to pay to get the integral. But once you have the integral, you can do many interesting things. And in particular, you can use integral to approximate sums. And think of the Euler-Maclaurin formula, for instance, or even really finite integrals and finite sums. So there is an interplay between discrete objects, Riemann sums, and the continuous object, which is the Riemann integral. And if you think about it historically, in fact, before Riemann, the integral existed, but mostly it was seen just like as the antiderivative. So you could define the integral as the antiderivative. So the integral of blah, blah, blah is the thing that when you take its derivative gives the function. And this was the view of mostly Euler and many, well, up to Euler and even afterwards. But this has to be, this is not totally correct, because Archimedes, for instance, computed volumes and surfaces and all that by splitting things and essentially doing what we would call Riemann sums. But nevertheless, for a long time, you know, when people were solving differential equations or whatever, they had this view that this was this was finding an antiderivative, even if Euler used the Euler scheme that we shall come back to. So we could define the integral as the antiderivative, but of course, it would be a pity not to know the relationship with sums, and that's bad. Another example that is probably familiar to you is the case of random walks. So you imagine you take the simple random walk, so probability 1/2 you go to the left, probability 1/2 you go to the right, and you study this thing. And again, this is an extremely simple object to define, even if you can ask questions about it that are very hard to answer. And it turns out that, in fact, if you look at this simple random walk, or basically at any random walk with a second moment, and you look at it from far away, well, what you will see is an object in the continuum which is Brownian motion. And again, Brownian motion is something which is more complicated to define than the random walk, but at the same time, it's much more flexible because it's in continuous time. You can make changes of variables. You have Ito's formula, just like you have had the change of variable formula for integrals, which make them more manageable than sums. Exactly the same. You have this object in the continuum, Brownian motion, which is much more flexible, and you can use this object in the continuum to prove things about random walks which are totally non-trivial. And to give just one example, for instance, the law of the iterated logarithm for random walks is proven by first proving it for the Brownian motion and then using some principles. So there is some kind of interplay between random walks and Brownian motion. It's totally possible to define Brownian motion as a limit of random walks. Take this as a definition of Brownian motion, but it's also possible to define it, well, somehow more abstractly by saying that it has independent increments and that it's a Gaussian process. So the increments are Gaussian and independent. And if you see the definition, this abstract definition that it's a Gaussian process with independent increments, of course, the relationship with random walks is not totally visible to start with, but it would be a pity to think of Brownian motion without knowing that it's related to random walks. Okay, so now Raph's theory falls really into this category that, well, let me say one more thing. In fact, basically, as I said, any random walk with vanishing mean and a second moment, when you look at it in the large, it's a Brownian motion. There is universality in this game. And in fact, somehow, it's a remarkable fact that you can say something at many, many objects by looking at only one. And Raph's theory is also something that is built basically to deal with such a situation. And To motivate it, in fact, this is even simpler than random walks somehow. It's just the following. So you imagine that you have a certain object Q. It's just a function which goes from AB, let's say, to R, let's say RK. So it's a function with K components. So you have Q1, Qk, and then you can take, imagine that this one is, well, let's say it's continuous or whatever, or integral. Well, let's say it's C1, so it has a derivative, and then you can construct iterated integrals. Okay. And those, so how do I define iterated integrals? It's just, so these are tensors, and they are given by integrating for, let's say, let's do it on the full interval, but we could do it on a subinterval. So we take k points, I'm sorry, s n points. I'm not happy with that. So let's call this one n, and let's take k integrals. I prefer that. And you dx I1 s1 dx ik sk. So if this is I'm sorry, this is not an x, this is a q. So this is what I call iterated integral. Okay, and so this, if q is differentiable, you define it just, you take this as a definition somehow if you want. It's just the integral dq I1 over ds evaluated at S1 dq ik over ds evaluated at sk d s1 sk, and again you put the same bounds s1. This you take as a definition somehow. Okay. So you have these objects at your disposal, and now you can say, okay, now what happens in the following situation, that you imagine that you are in a physical problem and there is some parameter. So you imagine that now that you have a family Q of epsilon, or positive epsilon, of smooth maps. I use the term smooth for C1 for me. If you do differential geometry, usually what you call smooth is C infinite, but what I call smooth is just C1. Now smooth maps, and you ask what happens at small epsilon. And then it turns out that there is a whole zoo of things that may happen. So the first thing is, first of all, if
Sorry.
Yes.
With respect to epsilon or respect to S1 SK?
To S1 SK. They depend on epsilon. S of epsilon smooth in S. And so the first thing you would ask basically is the following, that you would ask that this, which is defined as Q, exists. And of course, as you know, there are, for maps or paths, there are many definitions of what a limit means, but let's take it very, let's be very vague. There is no need to be more precise at the moment. And then, well, if it exists in a very strong sense, of course, things will go well, but then, but what about iterated integrals? To assume, so this is an assumption. What about iterated integrals? And basically, that's the one of the sources of half-path theory. So before we tackle this, let's look at something which is of the same kind, but which is extremely familiar to all of us, which is the following. Suppose you are in the plane. As you will see, I'm totally unable to draw a square, but let's pretend I can. So I draw the square, and then I draw the diagonal. Okay, and I would like now to approximate it using.
What is y?
I'm sorry?
X, y.
Well, if you want, x, y.
No, I'm asking what is x, what are the axes?
It's just a unit. It's
okay.
Just a square.
Anything. Okay.
Anything. Yeah. And I want to approximate the diagonal using a part on the lattice. So if the measure of the lattice is 1, the best I can do to approximate the diagonal is to do that. So this is mesh 1. Now if I use mesh 1/2, of course, I can do slightly better. And I can do this. So if I have other colors, excellent. I could also use the other side, but that's okay. So this is the one at mesh 1/2. And then I can go on, and of course, if I do it, let's do one more step. You already see that I'm a bad drawer, but anyway. So let's do another step. And you see that as the mesh gets small, the path gets closer to the diagonal. That's and in fact, it even, if you want to say things in mathematical terms, it converges uniformly. So really, if you look at the nth generation, you are never more than square root of 2 times 2 to the minus n on the diagonal. However, and that's what I guess you all know what I'm wanting to say. If you compute the length, however the length of the lattice path remains 2 instead of going to the length of the diagonal. Okay, whatever you do, You have to you are length 2 instead of square root of 2. And of course, you can imagine that there is any relevance to this situation that you have. Let's say, well, of course, if you would just look at the limiting approximation, you would just get this straight segment. And if you would forget about this problem with the length, you would lose something. And essentially, the analogy with half-path theory in the limit keep track not only of limiting path, the diagonal, but also of the anomalous length scale. So the limiting object would not be just the path, but something telling you, well, beware, when you measure length along this path, this is not the canonical length in the Euclidean plane, it's 8 times square root of 2. Okay. So you keep both, and then also make it, and then you make good use of it in applications. So this is the idea of half path. That in many interesting situations, you need to keep additional data in the continuum to really keep what is essential in the discrete. You cannot just get away and forget about all the details. There are some details that you have to keep, and this is really the simplest example that you can think of. So let's return now for a second.
Michel?
Yes.
You will keep the data about 2 and square root 2 in the diagonal or in the path? Which one are you going to modify?
Well, the limiting object is going to be made of two things, the diagonal and the square root of 2 in that simple case. And the square root of 2 being understood to be the anomalous scale. Okay?
So the Euclidean length is not continuous with respect to the convergence.
Yes, exactly.
So isn't there another notion of distance in the plane which would not be rotation invariance, in which the length of the diagonal would be 2?
Well, if you can choose whatever length.
L1 norm or.
Well, yes, I agree with you. If you would use the norm, which is the sum of the sum, not the square root of the sum of squares, but just the sum of the absolute values. So it would be the what is it? It's the L1, L infinity in that case. Well, it's one of the two. Well, anyway, well, yes, it would give exactly that.
This one would be continuous with respect to.
Yes. Well, but for this simple example that I showed, but I'm pretty sure I could get it to be discontinuous for other things. So, yeah, okay, but I agree. I had in mind that I wanted to see this as a Euclidean plane with the usual distance, and I'm just observing that sometimes going to the limit doesn't behave well with respect to integrals. The distance is obtained by computing an integral, and if I've not thought about it, but I'm pretty sure that with any notion of distance, I could cook up examples in which convergence doesn't lead to. okay, so what about iterated integrals? And then, so you imagine that this exists, and what can happen to integrals? But then, well, this is, as you may imagine, you have at least two things, and they are somehow related, that may happen. The first one is the following. Situation one. And assume, I'm sorry, I will assume as well, and assume that they converge as well. So you have your Q, you have this collection of objects, and you assume that when you take the limit, well, all these things do have a limit. And the situation one is the following. You can have that Q, the limit is smooth. But the limits of iterated integrals are not the limits, the iterated integrals of the limit. In situation two, Q is wide enough, the limit is wide enough, but its iterated integrals do not make sense. You see, to make sense naively of this object, I had to say, okay, let's so imagine this is smooth, I can take the derivative, and then I view this simply as Riemann integrals. But now you can very well imagine that even if this limit here is taken in a rather strong sense, not too strong, but rather strong sense, it may be that the limit is wide. And one simple example is that, for instance, you can approximate Brownian motion by parts which are differentiable, or at least piecewise differentiable, or by a random walk or whatever, which you can view. You can, if you have a random walk, you can just view it as a differentiable except at the corners. So this would make sense for if Q was given by a random walk, and you would just connect the different steps by straight lines. This would make perfect sense as well.
Just by so you have integrated integral. So you say, okay, Q is or your Q epsilon are smooth, but when you use dq, so you are integrated naively. You are doing a derivative and then an anti-derivative. So to me, it looks that you don't have an issue. Or is it because you multiply? You are multiplying derivatives.
Well, yes. Well, we'll see examples. Yes. In fact, the first rough path that I will show you, it will be one of these situations where Q epsilon is it's extremely simple. So Q epsilon, it's something that is hard to imagine in one dimensions. You have to be. It takes it.
So first of all, I have no issue when I take k equals 0 in your because I would do integral of dq from a to b, and so that would just be for me the difference of.
Yes, that's fine. That's fine.
But
The next, if you think about the next one, it's already you're already in trouble.
And is it real that you have a multidimensional object, or like it's already?
Well, if you don't have a multidimensional object, you can always. So you see, you can always decrete for one-dimensional object. You can always decrete that this is qb minus qa to the k divided by a factorial of k. But even in that case, you could imagine. You see, this is fine, but if the limit q epsilon of q epsilon is irregular, it wouldn't. These integrals wouldn't make sense at all. I mean, you wouldn't think of it. Okay, so let's answer this question. How do you make sense? So, as you mentioned, the first integral, it's easy to take. So imagine you want just to take the integral from a to b, integral from a to u dx v dqv dqu. This is the second iterated integral written slightly differently. And I agree with you that it's hard to imagine that this should be something different from qu minus qa. So this is integral from a to b qu minus qa u. And then, well, in that case, I already, at least if I, well, of course I could decide that I take this as a value, but if I really want to compute it honestly, if I don't have any regularity in Q, I don't know how to do it. We will see examples, many examples. But this is, well, yeah.
So your dqu, you cannot say that it's dqu square.
Well, okay, but then you're, okay, I agree with you. In one dimension, you can. As soon as you have two indices, you're lost.
Okay, so
okay, but in one dimension, you could. But doing so is just like you're just putting yourself in the position of Euler, which is not too bad, which is that integration is anti-derivation, forgetting that what we would like to have is an independent definition of this object, not something that it's the anti-derivative of something. You see, for Euler, the fact that the integral is the antiderivative is a definition, but after Riemann, it's a theorem. It's a theorem about it's a fundamental theorem of calculus. Yes. Okay. So if you doing so, you would put yourself in the situation of Euler. Again, I would buy it immediately if you asked me, but yes.
Just a quick question for the two situations. In both cases, we assume that, we assume that for all k, all order in the dimension, they all have.
You can imagine that you cut at some. You could imagine looking just at k equals 2. You just look at part of it, and in fact that's okay. So let's make already. In fact, it turns out that in many interesting situations, what is important is just the first few of these guys, and it's a situation which is very reminiscent in a somehow trivial case of what happens in quantum field theory when you have a renormalizable theory, which means you have only a finite number of objects that you need to deal with, and once you've understood them, some finite number of correlation functions that cause problems, and once you've cured them, all the other ones you get for free. Of course, computing them is just another story, but from the principles, okay. Yaron?
You're only interested in some simple integrals. For example, the example you gave is the length.
Yes.
The root of 1q prime square.
Yes.
No, it's more complicated.
In that case, we just look at these simple things. But you can do many things by solving, by iterative integrals. You can already do many things. Okay, and so somehow, half-past theory. So you see that And in this situation too, it's also the case that you can imagine two different families, Q epsilon, they converge to the same Q, but the iterated integrals, they converge, but they converge to different things. So there is even, well, the point is that the relation between Q and its iterated integrals, it's somehow clear if Q is smooth. If Q is not smooth, you cannot just, if you just say, okay, Q is not smooth, I just approximate it by smooth objects, I manage that the iterated integrals are defined, have a limit, and I take this as a definition. In fact, it's not perfect, because if you do so, you will see that this depends on the approximation scheme you've chosen for Q. There is no universal solution to that. Okay. Before,
Sorry,
yes.
This situation 0 and everything is fine. Q is smooth, the limits converge.
Sorry?
There could be a situation 0 where Q is smooth, the limits of the iterated integrals are the limits of the.
Yes, sure. Oh, yes, sure. But that, okay, but then.
Interesting. So
Well, I agree with you. There is situation 0. You are perfectly right.
you will address situation 1.
I'm sorry?
You will give some. What you're going to say is a way to address situation 1 and 2.
Yes, exactly. Yes. And in fact, I address situation 1 and 2 in a way that in situation 0, I do not do anything crazy. So I will give a way to address, half-path theory gives a way to address these situations, and in fact, if you apply it to situation 0, it doesn't do any harmful thing. Okay. So the main character in many things we are going to say are a few of these iterated integrals, but I will go to something which looks different, which is called controlled differential equations. And you will soon see that, in fact, these iterated integrals play an important role in that subject too. Okay, so it's nevertheless, if you have questions, it's well, maybe it's a nice point to stop. Well, no, I can proceed. Okay, so what is a controlled differential equation? Of course, this is a complicated way to say something simple. It's just you imagine that you are trying to solve something which is something like dyt is, if I take my notation, v of dt xt dxt. And so I imagine that, for instance, x goes from AB to a certain vector space E, and y goes from AB, so is known, y to a certain vector space F is the unknown. And to make sense, we view this V yt is a linear map for fixed, well, let's say V of xy is a linear, is for fixed xy, a linear map from E to F. So I could put indices, and if I put indices, so how I name the indices in this. So with indices, this would be equivalent. You will see. So if you think this is a little bit fancy, so this would just be that for you would have dy mu is equal to v mu I xt yt d x d phi. And if I will mostly use the Einstein summation convention that when I have indices down and up, I sum over them. But let's put the summation. So this is, and this will be true for me equals 1 to d, which is equal to the dimension of f, and n is the dimension. Okay, so it's essentially equivalent to us. Okay, so so if you think about it a priori, this is a formula somehow, but we have not made sense of it. And one way to make sense of it when x is smooth again is that you define v tilde, so e tilde of yt and t, we define it just to be v of let's say xt d t over dt, and then this equation will become equivalent to dyt over dt is equal to v tilde of yt, which is an ordinary differential equation. We're applying the same kind of trick as the one we applied here to define these iterated integrals by saying that this is going to be. I'm just doing something stupid. Well, rather stupid. This is the way to make sense of it. But I would like to say that when I say that these two things are equivalent, somehow I do not really say something like that. What I'm saying is that I interpret this equation as being that. This is an interpretation. I'm related something that is not defined a priori. I don't know what this means, and I relate it to something which is defined as soon as we've defined ordinary differential equations. And just to give one example of
you have a question.
yes,
I guess that there is a mismatch between v of x and y and v of yx.
yes, you're perfectly right.
No, it's not me. It's Sanjay. Also in the second, in the matrix form.
Yes. And I don't know. Yes, I decided to put the y.
And by the way, on the v tilde, you are missing the second argument.
No.
No?
It's t. No. You see, I replaced.
Okay. Sorry.
These are given functions of t, so this is just.
Sorry. This is not Sanjay. This was me. The wrong state.
Excellent. No, but you're right to ask. I mean, it's okay. So let's give one example that we are all familiar with of this situation. Or all, well, I say all familiar. Many of us are familiar with it. As an example, stochastic differential equations. So we would take xt to be a two-dimensional object which is bt and t. B is a Brownian motion. and then we would get something like dyt is little v of yt. I take I'm just giving an example. And the second is sigma of yt dbt, which is this is called the diffusion. Okay, so this is an example. One of the functions x is Brownian. The second one is time itself. And I'm looking at this equation. And this leads to, okay, so, and then the way this is usually dealt with is the following. You say, okay, I'm going to say that this is, let's say, little y at time. Let's say let's imagine that I take t. I take t is in 0% t. Just make it simple, and then I would transform this equation into this, which is integral from 0 to t v of ys ds plus integral of 0 to t sigma of ys dds. But okay, so just to make contact, so this is mathematicians. And if you look at it from the point of view of physics, you would say, okay, why bother? Let's write it as yt dot is v of yt plus sigma of yt psi t, and this is going to be a white noise. And then the question is, how do we decide whether this has a solution or not? And mathematicians would say that this has a solution if there is some kind of solution to this integral equation. So for that to be true, those two things have to be defined. And then you have to check that the left-hand side is equal to the right-hand side. But you have to define it, so it needs to make sense. And this is usually done by stochastic integration. And I will make a remark, let's say, for the expert somehow, which is that this defines, this is not what we call a pathways definition. So stochastic integration is going to approximate such objects by discrete ones, just like the Riemann integral. But what we ask for the discretization is to converge not in a pathway sense for every realization of Brownian motion, but in mean square. Okay. So I do not claim that if you give me one Brownian sample, I'm able to exhibit you a solution. What I'm saying is that I have the collection of all Brownian samples, I use it, and I show convergence in mean square. I'm sorry? Alors, je ne sais pas si je dirais les choses comme ça, mais oui, ça ressemble un petit peu à ça. Ouais.
This order depends on time here, so
Yes.
it doesn't matter.
Yes.
If you take a discrete time formalism and you replace the Brownian motion by a random walk, say a lattice random walk,
Yes.
then it would make sense
Yes, that's correct. Yes, that's correct. You're right, but first of all, it may.
You will have to tell what you call sigma and dB.
Yes, but once you've told it, it will be it will be fine. Yes, you well, yeah. The point is that doing so is well again, this would be going back to random walks, whereas we agree that somehow Brownian motion is easier to manipulate. You can make changes of variables and all that. So, for instance, proving using discretizations that many formulae would be awkward. But I agree with you, and in fact, it's even true that pathwise, that's correct. I mean, we will in fact wait for an example. We will see what happens if you try to discretize these things. Yes.
I want to iterate on Mark's question, but if you do pathwise, don't you get into these Ito-Stratonovich problems also?
Well, I will show you.
You have to give a kind of prescription.
Yes, and I will show you how it works and how it inspires what Harpas theory. That's one of the goals.
Oui, quand je vois ça, je pense toujours à une espèce d'intégrale de Wiener que je fais.
Oui, Ito Wiener, oui. Alors Wiener, ouais, bon, ok. Il y a une petite subtilité que Wiener, il avait défini ça uniquement quand l'objet qui était ici n'était pas aléatoire, et Ito, il a fait ça quand l'objet ici est aléatoire aussi. Mais oui, c'est une intégrale, c'est typiquement une généralisation de l'intégrale de Wiener.
English.
So, oh, thank you. Okay. Okay, so to say, okay, maybe it's worth saying it a little bit differently. If you do stochastic integration, you do discretization, and what you say is that when the mesh is small, you have a high probability that this is close to something, which is not to say the same as saying that for any sample you go close to something. It says that with high, yeah. It's when you discretize and you say, okay, when the mesh is small, there is a high probability that this object will be close to a limit, and which is not the same as doing pathwise integration. Okay, and in fact, half-path theory insists on pathwise constructions. Okay, so the solution given, which is very useful given by the Ito stochastic integration, is not the one half-path theory is after, and it turns out that there is a certain intersection on which the two approaches agree, but there are things half-path theory can do that stochastic integration cannot, and conversely, there are things in stochastic integration can do that half-path theory cannot do. So it's, and it's 11, so I can stop here for the first.
We can stop 10 minutes.
Yes. Okay.
Starting from now. So
yes.
We will come back at
11:10.
Yes. Thank you.
And this motivates me to say be just slightly more precise here about what I told about stochastic integration. So this is the following. Imagine, so this is just a side remark. In fact, before I say that, just what I will do here for half-path theory and half-path integration and all that, this is much less demanding than stochastic integration à la Ito. This is really an elementary theory. After that, mathematicians have done deep things with half-path, but the integration theory and what I will tell you about is really elementary, and it's not comparable in complexity with Ito integration theory from the point of view of the depth of mathematics. So, but nevertheless, imagine that you want to compute something which is as simple as the integral from 0 to 1 of bs dbs, and you imagine that B is a Brownian motion. Okay, so if I want to be fair, I would imagine that I have a probability space, omega, and I have samples. And I'm trying to compute this dBs of omega. So what am I going to do? One of the possibilities, for instance, is to take the simplest discretization, which is the following. I imagine that I say that this is approximately sum from m equals 0 to n minus 1 of b taken at time m over n omega, and making a convention. I'm used to Ito, but making a convention. In fact, the point that a convention is needed is not so obvious, but I do it that way, minus b m over n. I said that this is an approximation, and of course these guys depend on omega. And now I can ask many questions. For instance, does this converge for a given omega when n goes to infinity? So this is pathwise convergence. So imagine that I call this I, and I call this IN, is IN of omega going to a limit for every omega, or almost every omega. So this is what I call pathways. And then mean square is IN of omega minus something square. Okay, so I would like to take, I'm sorry. So I have this probability space here, and there is a probability measure here, and this integral dp of omega IN of omega minus something of omega squared going to 0. Okay, so this is what I call mean square. This quantity here could go to a limit when I fix omega and I let n go to infinity, or maybe it fails to do so, but nevertheless, if I look with so you see, this gets small, which means that with a high probability, IN of omega is close to this object that I just not really given a name to. Okay. And so really, what Rafa's theory is about is trying to make sense of things in this way, for this situation.
Okay, sorry. The second integral is a path integral now, dp of omega.
You can call it a path integral, but this is a probability space, and you have a probability measure, so you integrate over the probability. Yes, you could evaluate.
Omega is a realization.
Sorry?
Omega is a realization of the boundary.
Yes, but so you as a physicist you could see it as a Brownian as a path integral, but it's just you take the expectation with respect to a measure, and you have probability measure. It's just like it's just an ordinary probability space. But indeed, as a physicist, you might find a representation for this as a path integral. But here I just want to see I have a probability space. When I have a probability space, it means that I have a way to measure sets. And when I have a way to measure sets, I can also integrate functions and do that. So that's okay. I hope this clarifies a little bit. And if it doesn't, again, ask questions. I mean, I see that I'm already extremely late with respect to what I wanted to do, but that's not an issue. I don't care. The less I'm able to say, the less I have to prepare for the next time. So for me, it's 100% benefits. But I would nevertheless like to be able to. So I will look at the one dimension, the 1D case. 1D is very convenient because it avoids using indices and all that, or using complicated notations. It's a bit misleading at some point, but nevertheless, let's forget about it. So what we're trying to do is we are trying to make sense of this simple thing. Of course, if you look at it, this is just the same, but this time x is just from AB to R, and y as well. And v is just a function from R to R. This is very easy.
You are dropping the dependency of V on the.
Yes, just for simplicity. I'm going to put it just for simplicity, because again, it simplifies things, and it's quite natural. In fact, you will see this plays the fact that we do not include x there plays a role in the discussions. Okay, so now we want to try to solve it via an iterative scheme. And we are going to use Euler. So to use Euler efficiently, there is one very simple thing, which is the following. So imagine now that you have this object here, and be extremely naive. If f is a function, apply the stupid rules of differential calculus to get that df of yt is going to be equal to, I hope I will do it right. So this is going to be f prime of yt, dyt, so this is v of yt, dxt, okay? And go to an integral. So this would tell us that f of yt is going to be f of ya if I start at a. Well, okay, let's start at s plus integral from s to t f prime of yu v of yu dxu. Okay? So of course, as I've said nothing about the regularity of x, this is problematic because I have no idea of what this means at the moment. Okay? But now I can say, okay, this is just mathematics, this is ill-defined, who cares? Let's just say, okay, now I expect that if things are nice, I can just, if S is close enough to T, just approximate yu, v of yu, say that this is just going to be equal to approximated by, let's say, f prime of ys, v of ys. Okay, so get an approximation. To get an approximation, which is going to be that f of yt is approximately equal to f of ys plus integral from, I'm sorry. So now we are going to apply the Jeremy's rule, that if this is a constant, we take it out of the integral. If we replace this by the value at s, we take it out of the integral, and then we decide that the integral from s to t of dxu is equal to xt minus ft. So this is Jeremy's rule. And we are led to an approximation. So this is going to be f prime of ys, v of ys, xt minus xs. And then if you imagine that a equals t0, let's say, less than t1, less than tn, less than b, we are going to apply this, solve numerically, to get f of t m plus 1 is going to be equal, I'm sorry, f of y at tm plus 1 is going to be equal to f y tm plus f prime of y tm, v of y at tm, xtm plus 1 minus xtm. Okay, so this is called the Euler scheme. And the question now is, if I do that, but then I refine this subdivision enough, does this lead to a convergent? So this I call a subdivision delta. The mesh delta, I define it formally, but you say this is just the sub of tm plus 1 minus tm equals 0 to n minus 1. So this is just the mesh of the subdivision. And question, is this convergent, a convergent procedure when mesh delta goes down to 0? And if it works, then we have a good substitute. Why bothering doing some complicated integration theory? I solve numerically, and who cares? And yes. Well, I'm sorry. I can. No, it's just a way to. Well, I'm sorry. You're right. You got a point. What I'm really interested in. Okay, so I've mixed a little bit two things. So what I'm really interested in is just do it for y. So ytm plus 1 is ytm plus. Then this would be 1. So this is ytm xtm plus 1 minus xtm. I do it for this. I'm sorry. And the question is, that's a perfectly legitimate question. And then this makes sense, but I don't know how to iterate it. Okay, this one you agree I can iterate. Thank you. And again, we've already gone down to the one-dimensional case, but we will go to an even simpler thing, which is the following. Just take example v of y is equal to y. So it's the identity function. Okay, so this is the scheme. So we are saying that ytm plus 1 is equal to ytm times 1 plus so this is the thing we are going to look at. And the point is the following. So we shall make an assumption. It's that x is continuous. Xt is continuous in T. To start with. Okay. And then you can imagine that when the mesh is small enough, we can estimate that xtm plus 1 minus xtn is going to be an absolute value less than 1, so that this is always going to be a positive number. And we can exponentiate. And so what we would get is that log of yn plus 1 divided by ya is going to be just e to the sum log, I'm sorry, from L. I'm solving this equation, L equals 0 to n minus y, 1 log 1 plus xtl minus xtl plus 1 minus xtl is already a log.
Enlève le log à gauche.
Ah, merci. Okay, and then so it's a little exercise with inequalities. For instance, so let's take it as c plus 1. So okay, so let's just be rude that log 1 plus x, it's going to be if I say something, if I'm not totally stupid, and I subtract x, and this is going to be larger than minus x2, and this is to be going to be smaller than minus x2 over 3. This is crude, and this is valid. Let's say how do I say? So imagine that this is, you take x in absolute value less than 1/2. So this is a little inequality. And then you see that this sum here bon, on n'y arrive pas. So what do I get? I get that ytm divided by ya is going to be e to the x tm minus xa plus something, and something is between some from n equals 0 to l equals 0 to m minus 1 x t m l plus 1 minus x l squared minus 1/3 and minus some x plus 1 minus x l. I'm sorry, this is power 2, this is a power 2. This, okay, this is it. Okay, so now you see we are facing a little problem, which is what happens to this guy. And now we are going to use a little theorem that is maybe not so well known, is that if x is a continuous function, there are subdivisions delta, arbitrary small mesh, such that delta is as small as we please. And Q delta, I'm sorry, Q delta, I define it to be this quantity. I put a little index M. I'm sorry. I will define Q delta. This leads me to define Q delta is just equal to sum from 0 to n minus 1. You see this, the more points if I increase M up to n, this is going to increase. So let's look at this one, just the last one. So you see, if I'm in this situation,
Sorry, I cannot read your indices. Q delta is the sum.
it's the sum from m equals 0 to n minus 1 x
T plus 1 minus Tm.
x m plus n minus t. Okay, so now I use this little theorem. I can give you a reference for it. So this can be arbitrarily small. So you see, I can find subdivisions for which this is very small. For which this is very small, so this is well approximated just by xtm minus xa. And then either this holds for any subdivision which with small enough mesh, and then I'm happy, or it doesn't hold, and then I'm lost. So there is a dichotomy.
So in your theorem, F should be X.
Yes. Dichotomy. Well, so if this is called the quadratic variation, so if the quadratic variation goes to 0 and mesh goes to 0, then what we get is that yt is going to be ya e to the x t minus xa, so is a limit. On the other hand, if this guy, if not, then you see, because of this encadrement, because of these bounds, you see that there is no way you will be convergent, because for imagine that there are subdivisions for which this remains larger than some epsilon, even if the mesh of the subdivision is very small. Then this here is going to prevent convergence. I know that for certain subdivisions, I can make this extremely small, and then this is the only possibility. This will remain. But if there are some for which this doesn't get arbitrarily small, then I will not know. I will hesitate between, well, what should I take here? Okay. So if not, then there may be no limit. There may be no limit. Choosing different sequences of subdivisions may lead to different results, or to no result at all. Okay. So you see, the question now is, so what can we do? So, X does not have vanishing quadratic variation. And the answer is, well, let's try to go one step further. Let's try to do an improved approximation.
So what do you call that quadratic variation? It's
The quadratic variation is Q delta. Does not go to zero at small mesh. And in fact, I should call it the two variation, in fact, if I would be. Yes, because if you have a subdivision, you can apply it to each part of the subdivision. So, you see, yes, I assume that it was continuous. I said it somewhere. Assumption xt is continuous in T. Well, the problem is that if it's not true that Q delta is small for every subdivision when the mesh is small, then you do not know which subdivision to choose to make your computation. Does that answer your question? What I'm saying is that it's the only possible limit for this equation, if there is one, is that this is the solution. And this can occur only if X has vanishing two variation. If not, I will be able if not, I will fail. And it would, of course, you could say, okay, I take my X and I take only subdivisions for which it works, but this would be extremely inconvenient. I mean, if I change X a little bit, you are lost. You have to start again your computations from scratch.
There are, it's not for all.
No, exactly. There are subdivisions for which it's very small, which means that the only possible limit is zero. It's not possible, there is no function for which this has a limit which is non-zero. If there is a limit, it's zero. And I will, in the note, you will find some observation. You might think that Brownian motion is a counterexample, but it's not.
But the Brownian motion has vanishing two variation.
Brownian motion doesn't. Okay, so maybe I shouldn't have said it at all. But where is my? Here it is. So let's do it. So let's go. Let's continue this example. And imagine now X is a Brownian motion. Then it's an easy computation that if you compute, so let me just take a notation. So let's do this computation quickly. So imagine that this means that xt minus xs is an n t minus s 0 Gaussian random variable. And independent of non-overlapping other increments. Okay. So the only thing we have to know about it, so we have that the expectation of xt minus xs is equal to 0, and the expectation of xt minus xs squared is equal to t minus s. Okay. And I use this notation expectation. The physicist would write it as average xt minus xs is equal to 0, blah, blah, blah. I use the mathematician's notation expectation. And another way to write it, can also be written integral dp of omega xt of omega minus xs of omega equal to 0. I have a probability measure I can integrate with respect to this measure. I integrate over the samples omega belonging to omega. Okay? So then it's easy to see that for Brownian motion, Q delta of x, this is equal to b minus a, because you see for each little, so this is equal to sum from m is 0 to n minus 1 to m plus 1 minus tm. This is equal to b minus a. And if you work a little bit using the properties of Gaussians, it's easy to see that the odd moments vanish, and the only thing you need to know for the rest is that, or this computation is that if I take the power 4, this is equal to 3 t minus s squared, and then you will easily see that E of Q delta of x minus b minus a squared, I guess it's just, if I'm not mistaken, 2 sum from m equals 0 to n minus 1 m plus 1 minus m squared. There is a little compensation, you don't see anything. Okay, and so in particular, this is less than twice b minus a mesh of delta. So this is really, if you've never done this computation, do it for yourself. It's easy. You use the fact that the increments are independent over non-overlapping intervals. So typically, yeah, this is easy. Okay. And so, which means that, so this is an example of convergence mean square. Q delta converges to b minus square in mean square. And okay.
But it doesn't converge to 0.
No, it converges to b minus a.
You don't really apply what you did before.
No. So,
Yes, it was totally.
well, it's. We'll see. Wait and see. Okay, so this is it. And in fact, from this is a standard. Okay, so this is an easy computation. And then there is a theorem. It's a general theorem of probability that, in fact, if delta n is a sequence given in advance, of subdivisions with a mesh of delta n going down to 0, then delta of x converges to b minus a pathwise. Okay, almost surely if you want. Okay, so imagine, so what you could say is that at least when x is Brownian motion, when x is Brownian motion, it would be tempting to say, okay, in fact, I can use this theorem, whatever subdivision I use. So then, in fact, if you look at it, when x is smaller, so let's me just fix epsilon other than 0. When x is smaller than some delta of epsilon, then in fact the log of 1 plus x minus x is less than minus 1/2 1 minus x squared is larger than minus 1/2 1 plus epsilon x squared. Okay, so this is just a refinement of the little thing we said before. And so if you apply this result, you will see that it seems that, in fact, what you get here is 1/2 t minus a when x is Brownian motion. And in fact, this is to be taken with a grain of salt. And the point is the following. The point is that if delta n is chosen in advance, this is okay. But one can, given omega, cook up subdivisions such that delta is arbitrarily small, that was my previous statement, that you can always cook up subdivisions with arbitrary small mesh such that this is arbitrarily small, but also others such that Q delta is arbitrarily large, in fact. So this is again a phenomenon we know very well in physics. It's just inversion of limits somehow. If I take delta n in advance, then I can choose essentially any Brownian sample and it's going to give this result. However, if I'm given the Brownian sample but I'm unlucky enough to take a sequence of subdivision which is bad, this will just oscillate between 0 and infinity. Okay. So fixed subdivisions take a Brownian sample, that's fine. Fix the Brownian sample and take a bad sequence of subdivisions, this will explode. Okay, this will not work. Okay. So now the question is, what can we do? And there is something very suspicious about this result. Somehow, if you think about it, it's that this result here is typically what you would expect from applying stochastic calculus somehow. But you see, we've manipulated everything as if we could use the standard rules of differentiation. Yes.
You have not exactly used the standard rules of differentiation. You went to the second order term. You went to the quadratic variation, which is precisely
Yes,
to that.
that's correct. However,
So why you should have to prove that the third order does not
No.
square.
the point is that I could, well, maybe this will be clearer, but not today because I don't have time. Oh yes, I still have. Well, okay, we'll see. No, the miracle that leads to this solution is just that the Euler scheme goes forward in time. So we really apply the Euler scheme implements the Ito convention without saying it. So. But this is nevertheless this is very suspicious. So what can we do if x doesn't have vanishing variation? And I have to go back to my previous formulae, and you see I had this formula telling me that f of yt is equal to f of ys plus integral from s to t f prime yu This was my formula, but of course I can naively iterate it. Now you see this guy here is again of the same kind. I can apply the same formula to it, and then what I get is that f of yt is equal to f of ys plus integral from s to t f of f prime of ys b of ys plus okay, I have to concentrate myself a little bit. Integral from s to u f prime of yv. So it's becoming a little bit messy. So let me take the formula. Just to be sure that I make no mistake, I prefer to have a look at it. Oh, yes, okay, no, I wasn't that bad. Prime. This is, you see, I'm applying the formula for f to this big guy here. So I take this guy here and I take its prime just like I took the prime here. And then we v of yu, this is the guy, dx v. And here I still have my dxu. You see? I iterate. And then again, okay, so this one I can take away, and this is just giving me back my first approximation. And here again, I approximate here. V equals S. What I get is then that I have y of yt is approximately equal to y of ys plus f prime of ys v of ys x xt minus xs. This is my previous approximation. I get a new order in my approximation, which is this big thing here that gets out of the integral. So so let me just be a bit short. F prime v evaluated at ys. And the integral from s less than v less than u less than t dx v dxu. And so this is one of our iterated integrals. Okay. So now you see we are so first of all, if x is smooth, then the usual Euler scheme is convergent as mesh of delta when mesh of delta goes to 0. And the improved, the second order Euler scheme, so which would be this. I call this the second order Euler scheme. This one would be better. It would is convergent mesh delta square when mesh delta goes to 0. This integral makes sense, and we are on the safe side. And now comes the somehow good surprise. But what if x is not smooth? The first possibility, in fact, the naive or smooth x is integral dxq dxv dxq from s v u t. This is v. This is 1/2 xt minus x squared. Why not take the same formula? And then if you do so, again, so the approximation you see would be this, and then you use inequalities, bounds for log 1 plus x squared over 2 minus x. So this is a big O of x cubed, as you know, but you can do little bounds, and then this shows that taking ytm plus 1 equals ytm times 1 plus xtm plus 1 minus xtm plus 1/2 xtm plus 1 minus xtm squared this is for the example dy equals to v dx leads to convergent procedure as soon as x has 0 free variation. What do I mean by free variation? It's just sum of x tm plus 1 minus x tm cubed, m equals 0 to n minus 1, goes to 0 when mesh delta goes down to 0.
You don't have a minus sign in front of 1/2?
Where?
When you're
No, why should I have a minus sign?
because
Ça se comprend.
okay, no, maybe this way. I missed the word.
C'était une bonne question. Okay, so this is a convergent procedure as long as this is, and the result y is equal to ya e to the minus x to minus x. And you see, and I insist again, we have used, this time we really have used standard computation of derivatives, because even if we didn't really, to start with, use Well, you see, in this formula, we really use several times naive differentiation to establish this formula. Okay. But in the end, we have the happy result that when this is small, when this goes to 0, and then it's a simple exercise to do the following. You can go, of course, as further as you wish. It's the following. You iterate the Born expansion. Use the formal rule that integral A S1 blah 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 S1 SK B x S1 x SK is equal to 1 over factorial of k xb minus xa to the k. This is a formal rule because it,
Michel,
yes.
when you say the solution is yt equal ya xt minus a, your previous expression, what do you do with the quadratic term?
Well, you take the log, because when you take the log, this is going to be eaten. Because this is the beginning of the exponential. This is, you see, this object here is
Okay.
order. So you iterate the Born expansion with the rule that this is true, and then show that if x has vanishing k variation, I do not define formally what it means to be the k variation. Here is the 3 variation. The 2 variation was before. I guess you can generalize to k easily. Then the kth order Euler scheme is converged for dy equals y dx is convergent, and yt is equal to ya e to the xt minus xa. So this is, you see, this is a good thing if you decide to, okay, so one point is that the higher this number is, the easier it is to have 0 variation with respect to this number. So if you have vanishing 2 variation, you're sure that you have vanishing 3 variation. This is trivial, and then 4 variation and whatever. So, and this is reassuring because imagine that you go too far in the Born expansion and you make the computation, you still get the same answer at the end. There is a minimal thing to do to get a convergence scheme, which depends on how wide x is. But as soon as you've reached a level of approximation for which the k variation is 0, then if you go one step further, you can, but you do not change the final result. Anyway, you will find that this is the solution. So it is natural that I take 2 more minutes, Ricardo, if you don't mind.
Yeah, I just wanted to ask you a stupid question. Why do you call this Born expansion?
Well, this is exactly the Born expansion. If you imagine you have a potential in quantum mechanics and you iterate, this is, well, I call it the Born expansion. Okay. Yeah, okay, this is a name. I agree. It's just because it looks familiar to me. Okay, so I take 2 more minutes for the following remark.
You have up to 5 minutes.
Okay, fine. It's more than enough. Now, x is Brownian motion has vanishing 3 variation. But Ito tells me that integral V U C D B V dBu. This is equal to minus one half BT minus BS squared minus one half T minus S. So this is the stochastic integral. What if I use this? If we use this for the second order Euler scheme. So this integral is not defined pathwise. You do this thing of what I exemplified on the other blackboard of convergence in mean squared, but in mean squared this is the correct answer. So what if we use this for the Euler scheme and the answer? So basically, what you are going to use is now this ytm plus 1 is equal to ytm, and this is going to be 1 plus x tm plus 1 is x tm plus 1 half x tm plus 1 minus x. I'm sorry. X is equal to b. It's Brownian xt squared. And then minus 1 half tm plus 1 minus tm. Well, you see, without surprise, I'm adding this term, but this is not going to. This is going to count as little as it can, and answer the sequence of approximation converges. Converges to this line for any sequence of subdivisions. Pathwise, we don't have yt is equal to ya equal to the xt minus xa minus 1 half minus a. So you see, you can view this as Stratanovich integral. I've done the integration naively. I've decided that this is this. Okay, this is just naive integration. And I do the iterations and I get the Stratanovich solution. I get a naive solution. But if I say, okay, Ito tells me I should take this for the iterated integral, what happens? Well, fair enough. What I get at the end is that the solution of my differential equation is again the Ito solution. So to summarize, because my 5 minutes are over, if you work with Brownian motion and you stop at the first Euler scheme, you find, under some restrictions and by some miracle, you find the Ito solution, even if you've made all the computations very naively, so did not use stochastic calculus, whatever. However, if you go to second order Euler scheme, if you use the Stratanovich convention to compute this guy, you get the Stratanovich solution, and it works pathwise. And if you use the Ito formula for this guy, then you find the Ito solution for this equation. And that's what you wanted. So the moral is that when X is irregular, there is no a priori meaning that can be given to this. Conventions can be made, and depending on the conventions, you get different solutions for the equation. I think I should stop here.
Questions in the room or in the virtual room? Kiron?
So Michel, the message is that at some place you have some arbitrary conventions to make.
Yes,
This you cannot avoid.
yes. And from the naive point of view I want to have, this is exactly as in quantum field theory. You have your quantum field theory, you have your Lagrangian, nothing is going to tell you what the mass is going to be in the end with respect to the bare parameters in your theory. You have to fix it, you have to fix the normalization of whatever wave function, whatever, and then you can have an answer. But you need to fix things. You need to fix certain normalizations. Yes.
And the number of things you need to fix is the order of the scheme.
Yes. Yes. Well, yes. For the second, -1. For the first order, there is the Jeremy rule that you are not going to violate. That the integral of dx is x.
Yeah.
This we do not
This
violate.
one you do not dispute.
Yeah, we do not dispute this one. But,
This one you dispute. The
Yes.
quadratic one you dispute.
yes, exactly.
I don't exactly know how to say my question, but it's more, I'm surprised that for X where it's not smooth, so you have different ways of picking how you should define the interval.
Yes.
And there we saw that for any order we get the same. So I mean, if X if you have to go to the kth order to
Yes. But you have to it's the case order, but you get the same solution as soon as you decide that this is your definition.
then yeah, what I mean is that you get the same solution for all this kind of. I mean, you get the Stratanovich one and not
Yes.
the Ito.
Yes.
So is there? I mean, so that means maybe there are some a class of way to define your integrals that are all similar to give you the same solution. I mean,
Yes. The point is that. Okay, so we shall come to that in the next lecture. But in fact, so another way to say things is you see, I had this formula for the second order. Of course, it's erased now. But I had this formula for the second order. I didn't know what I could make with the iterated integral. So I could say, okay, let's approximate this path which is not smooth by smooth path and see what happens. And then I could get essentially anything for this guy. Essentially, I'm saying. And then next time we shall uncover some important thing that this thing will satisfy whatever the definition. If I take Ito, Stratanovich, or the limit of what tells you to take the limit of the sequence of smooth functions, whatever I do, this here will have to satisfy a rule which is called the chain relation, which is very important, and which is we shall start with it on the next lecture. So it's not arbitrary. There is arbitrariness, but not complete arbitrariness. Just as in quantum field theory, where certain things are arbitrary but satisfy some consistency relations.
Michel, you have a written question
Where is it?
from Domenic.
So was the smoothness assumption related to X?
Oh. Okay. Well, the point is that when you do the exercise of taking the exponential, expanding, and blah, 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 you will see that for the scheme to be convergent, it is enough that typically X has vanishing tree variation, which is true for Brownian motion, in fact. But so the point is that you see, usually if you take smooth functions and you take higher and higher order Euler scheme, you get something which is better, which has better and better convergent properties, because in n steps, if you cut your interval in n steps, typically, if you take the first order, the convergence is 1 over n, second order it's 1 over n squared, blah, blah, blah. So you get better and better. Here, essentially, a similar thing happens. things get better up to a point where, well, before a certain point, things are not convergent, and they become convergent after you've chosen enough, a high enough order for approximation, and then it stabilizes. But we relax the smoothness condition just when we see that when we compute what happens, this is convergent, even if x is not very smooth, but is only has vanishing three variation or whatever. Does this answer your question, Domenico? Okay.
Another question?
Yes.
In theory, you don't really need to have any probability.
No.
This is just analysis.
Yes, this is just
No
analysis.
randomness a priori.
No, there is
You
no.
take the example of one emotion, but
Yes, because yes, no, sure. Who cares? It turns out, nevertheless, that Brownian motion is typically well.
continuous non-differentiable object.
Well, it's typically one of these examples where half-path theory would apply. And in fact, one of the big successes of half-path theory is of a descendant of half-path theory, which is called regularity structures. And this is how mathematicians are now able to tackle partial stochastic nonlinear partial stochastic differential equations. So, for instance, the KPZ Kardar-Parisi-Zhang equation has been now the existence of solutions and how they should behave, and the fact that they are indeed given by the naive log transformation. What's the name of this one? Yes, of course, transformation is now a theorem in mathematics, and this is really one of the uses of. So the point is that indeed there are other applications of half-path than to stochastic processes, but stochastic processes give just the nicest examples where you can apply it. Yes.
Maybe it's naive and I'm doing too many shortcuts, but if I look at the formula of the log this, you see that if you have the log of 1 plus x squared, if you keep all the terms, you have log of exponential of x minus x, so you have 0, so you have something. I mean, if you had x that had oral order in k, so never a vanishing k, I feel like it would still give us a finite result. It would still give us something. So,
well, okay. So in that case, that's fair because it's where I have chosen really a very simple differential equation. If you start trying to do the same thing, for instance, I'm asking that V has some regular, the one, what I use, this here, when I write down dx, dy is equal to V dx, V of y dx. When I do my approximations, so if I look at the first order Euler scheme, I don't have to make much assumptions on V, but at some point, next time I have to take a derivative of V, a second derivative and all that. So in the end, if I want to do what you want to do, you have to assume analyticity in V, and essentially you would say that V, so you would rewrite it dy over V. So we could do that in one dimension as the dy over dx, integrate on both sides. This is just V of y. You could decide that the solution. So this is something you could do, but in fact it's a dead end if you go to higher dimensions or for many reasons. And again, this would be like being back. There are many people who would like to be Euler in this room, but there is only one Euler. This is just saying that integration is anti-derivation, which is not the procedure we want to have. We want to have an iterative procedure with discretization to build integrals, and then we have a fundamental theorem of calculus. We don't want to throw away half of the theory. Does this answer your question?
Do you have theorems to state that the Kate variation is small without computing it? To control the Kate variation without computing it?
Well, first of all, if your function is differentiable, it has vanishing 2 variation, vanishing
Yeah,
3
okay,
variation,
yeah.
whatever. But apart from that, it's just somehow your question is to me looks a little bit like, is there a way to know that a function is differentiable without computing? Well,
Okay.
it's a bit of the same kind. I mean, no, well, Holder, for instance. Well, okay, there is maybe something
Holder,
which is
Holder.
easier. Just so
Sufficient conditions.
If-
Method.
X is alpha Holder, with alpha strictly larger than 1 over p, that's easy. X has vanishing p variation. So this is a little bit easier to check maybe than doing that, because here you have to make a complicated sum. This is something you can just verify locally. It means that if you come close to the point, so xt minus xs is bounded by some k t minus s to the alpha. So this is something you can maybe check in an easier way.
Okay, thank you.
We call it a day.
Okay, thank you, Michel.